Good evening everyone. Today we are going to discuss about the aromatic hydrocarbons and aromaticity. This is for the BSc students of second semester of Dibrugarh University or the BCHCT 131 paper and the earlier CHC05 paper of IGNOU. So the content is aromaticity and aromatic hydrocarbons. Well, we have so far discussed about the aliphatic hydrocarbons. The aliphatic hydrocarbons we have discussed so far are alkanes, alkenes, and alkynes. Now, what are the aromatic compounds and what makes the aromatic compounds different from these aliphatic compounds? So we'll have to discuss these things in this class, and the specific properties aromatic compounds have. We'll also discuss about this thing in this particular class. So let us start this class. So what is an aromatic compound? And aromatic compound is a compound which is particularly characterized by its smell. The smell it has is always unique. The smell you are getting from kerosene oil, it is unique. It is you obtain from the smell you obtain from naphthalene, it is unique. The naphthalene ball you use in the clothes, and again the what you say jasmine oil, all these are containing some aromatic compounds. That's why these are unique in smell. So there are some aromatic compounds always possess some specific smell. So the word aromatic comes from the Greek the aroma means fragrant smell. So the compound that contains fragrant smell are we may call as aromatic compounds. The first compound, aromatic compound, whenever we heard the term aromatic compound, the first compound comes to our mind is benzene. It is the structure of benzene I have shown in this slide. You may know the structure of this compound. The benzene, it is the simplest aromatic compound which was first isolated by Michael Faraday in 1825 from the gas obtained by pyrolysis of whale oil. Later in 1845, Holman discovered benzene in coal tar, which contains benzene and many of its derivatives. Okay. Regarding structure, benzene is a cyclic compound of 6 carbon atoms. It's a beautiful hexagonal flat molecule and as well as a symmetric molecule. The 6 carbon atoms, these are the 6 carbon atoms of the benzene are all sp2 hybridized. Since all the carbon atoms are sp2 hybridized, the molecule is expected to be a planar and actually it is a planar molecule. Okay. Now the unhybridized p orbital, every carbon atom has one unhybridized p orbital. That means every carbon atom has one unhybridized p orbital containing one electron each. So 6 electrons in 6 unused unhybridized p orbital. So these 6 electrons form a pi molecular cloud like this. This is a beautiful ring compound. The molecule has a CCC bond angle of 120 degrees as it contains sp2 hybridization. And one another thing you will find that the CC bond length, although one CC bond is single bond and another CC bond is double bond, alternate bonds are double bonds, alternate bonds are single bonds, but the overall CC bond is found to be 139 picometer. We'll see why it is in the next slides. Why it is so in the next slides. So the bond angle is 120 degree. All that I said, this is understandable. Okay. Now, what is resonance and aromaticity? Now, so see, alkene we have already discussed about alkenes. Alkenes contain a single double bond, pi bond. Contains a pi bond. Now, if you hydrogenate a double bond, it releases an amount of energy. So we term it as a delta H. For in cyclohexane, it behaves like as an alkene since cyclohexane contains only one double bond. If we hydrogenate in presence of nickel, this cyclohexane, then we will get the hydrogenation energy as minus 121 kilojoule per mole. That is the amount of energy released is 121 kilojoule per mole. Now see, benzene is containing 3 such double bonds. So we can expect how much amount of energy will be released in this case 3 into since it contains 3 double bonds, so 3 into minus 121, that is minus 363 kilojoule per mole energy should be released, but it has been found that the amount of energy released is only 209 kilojoule per mole. So this bounds us to conclude that cyclohexatrine is not a simple hexatrine, not a simple trine like an alkene. It is somewhat different. So the amount of energy by which it is less, for example, it should be minus, hypothetically it should be minus 363, but it is found to be minus 209. If we make a difference of these two value, then we will find it is that the difference is 154 kilojoule per mole. So this amount of energy is called the resonance energy. So this resonance energy makes benzene something different, not behaving like simple triene alkenes towards the addition reaction. So this energy difference is called the resonance energy and is responsible for the stability of the benzene compared to other unsaturated compounds. Because other unsaturated compounds are very prone to addition reactions, but benzene is not much prone to addition compounds. So benzene is more stable than the unsaturated compounds. So because unsaturated compounds are lacking of resonance stabilization, but here benzene has a resonance stabilization energy of 154 kilojoule per mole. Okay, going to the next slide. So we are discussing about the resonance energy or resonance. Kekulé proposed two structures, structure 1 and 2, for a resonance structure of benzene. The Kekulé structures says that the double bond position is not fixed. This may be sometimes here, sometimes here, sometimes here, sometimes here. Every position is possible for a double bond, but there should always be an alternate in bonds. So that means one single bond, one double bond, one single bond, one double bond, like this. So Kekulé proposed these two structures, 1 and 2. But another scientist known as Dewar, he proposed another three structures, 3, 4, and 5. These are also resonance structures of benzene. But later on, it has been found that the main two resonance structures are 1 and 2, which are contributing mainly to the resonance hybrid of benzene. That's why we are regarding now 1 and 2 as the main resonance structures of benzene. So these are 1 and 2. These are the main resonance structures of benzene proposed by Kekulé. So we can draw the resonance hybrid like this structure 6. That means we are putting a circle here in between the hexagon. This circle means that the position of the double bonds and single bonds are not fixed, they are always alternating towards to each other. Okay. Now we have already told you that benzene or benzene like compounds are having some stability towards addition reactions. They are not as much reactive as alkenes. So why it is so? The quality, it is because of resonance energy or some other else. So the quality that makes benzene or benzene like compounds stable is known as aromaticity. The quality which makes benzene like compounds so much stable towards the reactivity is known as aromaticity. So it is a quality of a compound that makes it stable. So how we can judge one molecule as an aromatic or a non-aromatic? So Eric Huckel proposed some rules to find out whether a molecule is aromatic or not. So we are here summarizing the rules in the red color. Here you see. So I'm going to read out the rules. Number 1, the structure must be cyclic. First. Second, each atom in the ring must have an unhybridized P orbital. Third, the molecule should be planar. That means if each carbon atom of your compound is sp2 hybridized, it should automatically be planar. Okay, the molecule should be planar. Thus, the unhybridized p orbitals must overlap to form a continuous ring of parallel orbitals, allowing for the most efficient overlap. Number 4, the number of pi electrons present in the unhybridized p orbitals must be equal to 4n plus 2, where n is any positive integer having the values 0, 1, 2, 3, etc. Okay. So let us apply. So the terms of aromaticities are very simple. Terms of aromaticity. So for a molecule to be aromatic, 3 preliminary criteria should be fulfilled. That is, molecule should be cyclic. Molecule should have all the sp2 atoms. And molecule should be planar. These two are contrary to each other, because if a molecule has all sp2 atoms, it is automatically be planar. Okay. Now, fourthly, we will have to see whether the number of molecules is number of pi electrons follows the 4n plus 2 or follows the 4n mathematical equation. If it follows 4n plus 2, then it will be said as aromatic. If it is 4n, then it will said be anti-aromatic. But if any one of the preliminary conditions are not satisfied among the cyclic sp2 or planar, if one of these is not satisfied, then it will be neither aromatic nor anti-aromatic, but in fact it will be non-aromatic. So let us see how it is so. Benzene, we know here 6 pi electrons. Remember the rules. Molecule is cyclic, yes, cyclic. Molecule is planar, yes, planar. Why? Because it has all the carbon atoms sp2 habits. Okay, up to this point it is okay. Now let us see the 4n plus 2 rule of Huckel. The number of pi electrons here is 1, 2, 3. 3 pi volts means 6 pi electrons. So 4n plus 2 is equal to 6. That means n is equal to 1. Well, good. It follows the 4n plus 2 rule. That means it follows Huckel's rule and therefore it is aromatic. Now let us go to the cyclopropene. The one of the fact that this is sp2 carbon, this is sp2 carbon, but this is not sp2 carbon, this is sp3 carbon. That means this, because of this carbon, the molecule is not planar. So among the 3 preliminary criteria, cyclic, planar, sp2 criteria, the 2 criteria are not satisfied. Therefore, we are not going to judge whether it is 4n or 4n plus 2 electrons, because one of the preliminary criteria are not satisfied. That means this molecule is non-aromatic, not aromatic. Now let us go to the cyclobutadiene. It is cyclic, planar, well satisfied. sp2, all the 3 preliminary criteria are satisfied. Now let us see the Huckel's criteria. That means 4n plus 2 is equal to 4. That means 4n plus 2 is equal to 4. So n will be a fraction. So it is not satisfied. That means it is not aromatic. But since it follows 4n rule, therefore it is anti-aromatic. Because 4n is equal to 4, n is equal to 1. Okay, good. Now let us see another example. This is called cyclooctatetrine. In the cyclooctatetrine, we are seeing here 8 pi electrons, but 8 pi electrons. This is cyclic, planar, sp2. So it follows 4n rule. Therefore, it should be anti-aromatic. But in fact, it has been found to be not aromatic. Why? Because although all the carbon atoms here are sp2 hybridized, but this molecule is not planar because the molecule is so much constrained that it cannot adopt planar shape. It's a small. It has to be there in a very small volume. That's why it follows tub-like shape like this, tub-like shape. So this becomes non-planar and exceptionally the molecule becomes non-aromatic. You will have to remember this exceptional case. Okay. This is more examples for your practice. You will practice. I think you will practice in the later. Now let us take another example. Anulins. Anulins are always some this type of cyclic compounds, but here the volume in between the molecule is very large. Therefore, the cavity in anulins is sufficiently large, and hence steric interactions cannot play any role in the case of aromaticity. Therefore, all the molecules are here aromatic as it follows 4n plus 2 rule. And molecule is not here not planar. The molecules are planar because of the large cavities present in between the molecule. Okay. These are heterocyclic aromatic compounds. You will see these are also following Huckel's rule. These are aromatic. These are some polynuclear aromatic hydrocarbons: naphthalene, anthracene, phenanthine. This is contain 10 pi electrons. This is contain 14 pi. This is contain 14 pi. All are satisfying 4n plus 2 rule. That is Huckel's rule. That's why they are aromatic. These are the homeworks for you. Which of the following species are aromatic? This is a multiple choice question. I am leaving it for you. You will see. You will always follow the rule: cyclic, planar, sp2, and then Huckel's rule. If it follows Huckel's rule, aromatic. Not follows, that is, it follows 4n rule, then it will be said as anti-aromatic. If the molecule does not follow the preliminary rule, one of the 3 preliminary rules, then it will be said as anti-aromatic. So next question is cyclooctatetrine is conjugated polyene, so that it should be aromatic, but in fact it has been found to be not aromatic. Why? I have already explained, because this molecule always try to adopt a non-planar shape because of the steric strain, and it becomes tub shaped and becomes non-planar, and since the molecule becomes non-planar, it cannot be aromatic. So the molecule is not aromatic. Okay, thank you very much. I have already told in this class about how to judge a molecule as a aromatic or not. So in the next class, we will see the properties of aromatics. If it does not show aromatic addition compound, then what type of reactions it can show, I will discuss in the next class. Thank you very much.